Hello everyone, my name is Dr. Arnav Samanto. Today my topic of discussion is aromaticity. This is a very small topic. So before coming to aromaticity, we should know about the aromatic compounds. The name aromatic comes from the Greek word aroma, which means fragrance. This connection to smell was the basis for naming this class of compounds. So aromatic compounds must have some smell or fragrance. And aromaticity is the basic chemical property of the aromatic compounds. What is aromaticity? Now, aromaticity is a chemical property that describes the increased stability of certain cyclic molecules due to the delocalization of electrons within the ring system. There are several criteria for compounds to be aromatic. First is molecule should be cyclic, second one is molecule should be planar, and in the ring all atoms have anhydride p orbitals, and there is complete delocalization of pi electrons over the complete ring. This is known as resonance. And aromatic compounds must contain 4n plus 2 pi electrons, where n is 0, 1, 2, 3 and so on. This rule is known as Huckel rule. If we consider a simple benzene molecule, the picture A represents the p orbital array and B represents the delocalization of pi electron above and below the benzene ring. So we have already discussed the Huckel rule. Huckel rule states that the aromatic compounds must contain 4n plus 2 pi electrons. If we consider benzene molecule, there are total 3 pi bonds. So 1 pi bonds means 2 electrons. So total 3 pi bonds. So total 6 pi electrons. So it follow the Huckel rule. If we consider the n is equal to 1, so total 4n plus 2 pi value is 6 pi electron. Apart from benzene molecule, there are some other aromatic systems also, like pyridine, pyrimidine, pyrrole, thiophene, furan. So for calculation of pi electron, if we consider the pyridine molecule, the lone pair of nitrogen do not participate in the conjugation process. So in this case, we do not consider the lone pair in the calculation of pi electron. But in case of thiophene or furan, the lone pair of sulfur or oxygen participate in the conjugation process. So in this case, for calculation of pi electron, we will consider the lone pair. So all are the 6 pi electron system. If n value is 2, then the 4n plus 2 pi value is 10 pi system. So there are several examples of the 10 pi electron system like quinoline, naphthalene, indole, etc. Similarly, in case of quinoline, the lone pair of nitrogen do not participate in the conjugation process, but in case of indole, the lone pair of nitrogen will participate in the conjugation process. So in this case, we will consider the lone pair for the calculation of pi electron. Apart from aromatic compounds, there are some organic compounds such as anti-aromatic compounds and non-aromatic compounds. So what is anti-aromatic compounds? So anti-aromatic compound should follow the following rules. First point is molecule should be cyclic, molecule should be planar, and complete delocalization of pi electron. So the first 3 points are same as of the aromatic compound. But apart from 4n plus 2 pi electrons, for aromatic compounds, the anti-aromatic compounds contain 4n pi electrons, where n value is 0, 1, 2, 3, so on. So it should be noted that an aromatic compound is more stable compared to an analogous cyclic compound with localized electrons, whereas an anti-aromatic compound is less stable compared to an analogous cyclic compound with localized electrons. Basically, 4n plus 2 pi system delocalization increases the stability of the ring, whereas in 4n pi system delocalization decreases the stability. And non-aromatic compounds are not aromatic due to reasons such as lack of planarity or disruption of delocalization. Non-aromatic compounds may contain either foreign pi electrons or foreign plus 2 pi electrons. So non-aromatic compound violates any one of the first 3 points. The first 3 point is key: molecule should be cyclic, molecule should be planar, and complete delocalization of pi electron. So non-aromatic compounds are non-planar. So due to non-planarity, the complete delocalization of pi electrons is not possible. So these are the differences between aromatic, anti-aromatic, and non-aromatic compounds. So first point, the aromatic and anti-aromatic compound both are cyclic and planar, but non-aromatic compound not necessarily cyclic, either cyclic or acyclic and non-planar. For aromatic and anti-aromatic compounds, there is complete delocalization of pi electrons, but in case of non-aromatic compounds, no complete delocalization of pi electrons. Aromatic compounds contain foreign plus 2 pi electrons, anti-aromatic compound contains foreign pi electrons, and non-aromatic compound contains either foreign pi or foreign plus 2 pi electrons. So for example, if we consider cyclopropene, cyclopropynyl cation and cyclopropynyl anion, we can see that in case of cyclopropene, it is cyclic, but it is non-planar because this carbon atom is no sp3 hybridized. But in case of cyclopropynyl cation, this carbon atom is positively charged, so it is sp2 hybridized, so it is planar and cyclic. Similar case occurs in case of cyclopropynyl anion. It is also planar and cyclic. So it should be remembered that if a carbon atom contains positive charge or negative charge, it should be sp3 hybridized and planar molecule. And for calculation of pi electrons, if there is one negative charge, so one negative charge means 2 pi electron, but in case of positive charge, there is no pi electron. Okay, so in this case, it is non-conjugated due to the loss of planarity. It is fully conjugated system, and it is also fully conjugated system, and it obey foreign plus 2 pi electron where n value is 0. So if n value is 0, that is it contains 2 pi electron system. And in case of cyclopropynyl cation, it is also obey the foreign plus 2 pi rule, and in case of cyclopropynyl anion, it obey foreign pi rule. So cyclopropene is non-aromatic, cyclopropynyl cation is aromatic, and cyclopropynyl anion is anti-aromatic. If we consider cyclobutadiene and cyclobutadienyl dication, so for both cases, these molecules are planar and cyclic. It is fully conjugated system, and it is also fully conjugated system. Here total electron is 2 pi total 4 pi electron system. In case of cyclobutadienyl dication, it contains only 2 pi electron system. So it is anti-aromatic, but it obey 4n plus 2 pi rule, so it is aromatic. So if we consider cyclopentadiene, cyclopentadienyl cation, and cyclopentadiene anion, so for cyclopentadiene, it is non-planar and cyclic, non-conjugated system, and it obey 4n pi rule. So it is non-aromatic. For cyclopentadienyl cation, it is planar, cyclic, fully conjugated system, and obey 4n pi rule. So it is anti-aromatic. But in case of cyclopentadiene anion, it is planar, cyclic, fully conjugated system, and here total 6 pi electron system. So it is aromatic. Further, if we consider cycloheptatriene, cycloheptatrienyl cation, and cycloheptatrienyl anion, For cycloheptatriene, it is non-planar and cyclic, non-conjugated system, and here total 6 pi e electron. So it is non-aromatic. For cyclopentatrienyl cation, it is planar, cyclic, fully conjugated system, and obey 4n plus 2 rule, as it contains 6 pi electrons, so it is aromatic. But in case of cyclopentatrienyl anion, it is planar, cyclic, fully conjugated system, but here total electron count is 8 pi electron system, so it is anti-aromatic. So there is some exception. If we consider cycloocta tetraene molecule, it is known as cot molecule. So cot molecule is apparently looks like planar and contains 8 pi electron system. So it is supposed to be anti-aromatic. But this molecule is actually non-planar and it has a tub-like shape. So due to the non-planarity, there is a disruption of conjugation of electrons. So cot molecule is non-aromatic. So thank you all.